This is Chapter 14, Lecture 1, Glaciers, Shorelines, and Changing Sea Levels. And for this lecture, we'll mostly just focus on glaciers. And our goals include basically an introduction and an ability to identify glacial processes and glacial features. We will also look at the causes of glaciations and the relationship between glaciers and sea level. And then in lecture 2, we'll get more into the processes, features, and hazards along shorelines, and we'll look at the causes and manifestations of sea level rise and fall. So starting out, this is not in your book exactly. These are some slides that I made. I was able to take a course on glacial geology at Grand Valley earlier in 2025. So that was with Dr. Pat Colgan, and I borrow some of his work here. So what is a glacier? A glacier is a permanent body of snow and ice that moves continuously under the influence of gravity. It's not sea ice or icebergs. We're mostly just moving on land here. And I have the Grinnell Glacier in that photo in Montana. This is during the summer. It's been shrinking in size, of course. We have the extent of it in 1850 over here to 1937, 1968, 1981, 2005, and then I'm not sure the exact date of this photo, but fairly recent. So, just looking at our Great Lakes region, let's talk about the Ice Age. So we're talking, say, 20,000 years ago. By 18,700 years ago, we have ice. It was covering this entire region of Michigan and beyond. And by 18,700 years ago, the ice is retreating back from its last glacial maximum position. When we say retreat, it just means that the ice is melting, and what's left behind are glacial lakes. So the ice continues to melt back about 16,200 years ago. Say Ottawa County in western Michigan would have been ice-free by this time. And then to 13,700 years ago, most of lower Michigan was ice-free. We call this Glacial Lake Chicago, which would later become Lake Michigan. And then by 11,700 years ago, the ice is almost gone from upper Michigan. And by 9,500 years ago, most of Michigan was ice-free. And that was our ice age, but we're still in it because we have these great ice sheets that cover parts of our planet still. We'll get into that later. I mentioned glacial lakes, or just the meltwater from glaciers. Now, those form at the end of a glacier as it melts. We also call the end of a glacier a terminus. So I've got some examples. We've got Southeast Iceland, currently has nice glacial lakes. Cloud Peak, Wyoming, that glacier is quickly disappearing with changing climate. And there is a glacial lake at the terminus of the glacier. Here's a glacier. And then, of course, our Great Lakes are glacial lakes. Glacial lakes have distinct sediments that are washed into them from the melting glacier. Why do we care about glacial lake deposits? Well, I'm assuming you're not too far from University Center, Michigan if you're taking this class with me. We're sitting on glacial lake deposits mostly, okay? So this is an old screenshot from GeoWebface back when Michigan's Eagle was called the DEQ. And the blue are lake clay, lacustrine lake, same thing, silt and sand and gravel, okay? Clay is abundant here due to weathering of what was the shale bedrock and then deposition in a glacial lake environment. Now, different parts of our former glaciers were called lobes. Like we had the Saginaw lobe, the Huron lobe, the Lake Michigan lobe, And as those melted, we got glacial lakes and their associated deposits. One associated deposit with a glacial lake is a moraine. It's kind of a ridge. It is a ridge usually. As a glacier melts, and this is an existing glacier in Iceland, it drops a mix of sediment in arched ridges. Okay, so at its terminus or at its end. So you have the glacier, and you have a glacial lake, but where it once was, it dropped these sediments as moraines. We can look at a cross section of a glacial lake bottom. Okay, so this would be the glacier. As the glacier melts, you get glacial water, current glacial lake, and our coarser sediments are deposited nearer to the glacier. It takes more energy to move those, so we'll see them here. As you go further out, you get finer sediments like mud, clayey mud, silt, finer sediment that way. And ultimately, this glacial lake drains via a river, not unlike the Saginaw Bay and the Saginaw River. It's a good analogy. When we see sand deposits in the sediment record, we think of those as either being from the lake itself or along the shoreline of a lake. That's my dog Molly. She's 18. Clay is associated with, deposition into the lake itself. Usually that's lake sediment. You sometimes could get what's called a drop stone interrupting the clay layers because you might have little floating pieces of ice in a glacial lake that carry larger clasts or particles, and they are deposited as well. You can also see some cyclic deposition in terms of varves or rhythmic depositions. We might also see from a glacier a mix of gravel, sand, and clay, and that could be our outer edge of a glacial lake or a moraine. We also call that a diamicton when you have an assemblage of sediments that are different sizes. This is an older map now. Michigan Geological Survey would like to update all of these across the state, but it gives us a basic idea of the so-called Ice Age geology of the Saginaw Bay area. So we have in blue, and I'll highlight that if the colors don't look right to you, lake, clay, and silt. We also have lake, sand, gravel, and mud. And then the yellow would be dune sand. And then the moraines, it's these linear deposits here. That would be a mix of gravel, sand, clay, silt. Okay, so like the terminus of the glacier would have dropped these in ridge form. I presented a little bit about glacial geology in terms of the landfills that I regulate in my day job. So this is a slide from that. We have a site in northern Bay County, and the landfill itself is right here. So I did this little Google Earth cross-section to show the elevation changes. We have the Port Huron Moraine Complex, quite a ridge here, and then we go down in elevation towards the coast, the Lake Huron coast. You actually see the landfill being a spike in elevation, and there's an old shoreline ridge here too, going down in elevation. This helps me understand, the former lake bottom that many of us live on. And then you can go from south to north through Bay City. Okay, so you have the Port Huron Moraine Complex. You see how much the color changes. There's a lot of good hunting through here. This is where a lot of the deer live because the habitat's so good for it, but it's an old moraine complex. We have a moraine here too. It's just harder to see. This is all agricultural land, mostly cleared. And you're going down, down, down in elevation until you get to Lake Huron. We have a little spike for our coal ash landfills along the coast and the mouth of the Saginaw River. But that's kind of what we're looking at. Our moraines are higher in elevation, and then the lake bottom, of course, is lower in elevation. So that was my part of it. These images will all be from your book now. We'll look at the topography of the northeastern U.S. and centered, of course, on our Great Lakes region. I mean, how could you not, right? So this is a shaded relief map. It shows the topographic features around the Great Lakes and the northeastern U.S. Okay, so we can look at different parts of the map to see the different features, larger, smaller, ridges, roughness of the terrain. All right. We see, of course, these are our glacial lakes. This is lower in elevation along the Saginaw Bay. We can actually see a ridge here, our moraine. And then, of course, the rest of Michigan is much more complex in topography. We're different along the eastern coast. We're different, yeah. So that's a smooth area versus rough areas, right? Okay, I didn't want to go that far ahead. But yeah, so you see that, say, along Long Island, Appalachia is rougher. Toward the Delaware Bay, it gets much smoother. Okay, so looking kind of centered on Minnesota and Wisconsin, we have troughs and ridges. So T and R. There's a ridge here as well. And the glaciers are responsible for much of this. So smooth troughs, curved ridges. Now if we look more central to the east, we see a trough here in Ohio to a ridge crossing into Indiana. Curved ridges, numerous lakes, of course, which I've already pointed out. And then if we look more so towards the northeast, right, this is the Appalachian Mountains. So that has its own unique history, which these were later shaped by glaciers as well. A lot of geologists ignore that. They think only about the rocks, and they don't care about how they were weathered. But for me, we have to look at the whole picture to really understand Earth history. Okay, so looking here, we have a smooth trough, right? Now it's a river valley, but it's a huge trough. And of course, rough areas, embayments in the coast. Okay, so tucked in here, it's quite complex. So that's just looking at a broad view. Let's think more so about the characteristics of a glacier. Okay, so a glacier is a moving mass of ice under gravity on land with rocks and finer sediment. You know, they're not clean. You shouldn't drink from a glacier, right? It's carrying all this sediment. Many glaciers begin in snowfields in higher elevations or at higher latitudes. Basically, what you need to create a glacier is cold enough temperature and sufficient precipitation to form this. And it really becomes a glacier if the snowpack doesn't melt within a given calendar year. You keep adding to the glacier with more snowfall. So snow then turns into blue ice as it gets buried and compressed. These glaciers can cover broad areas or they can be confined to valleys. And there's different names for glaciers based on where they're found and how they are shaped. So we can have grooves, ridges, and sediment-rich streaks forming by flow within the glacier. And the glaciers can become confined within valleys, and some valley glaciers merge to produce a wider mass of flowing ice. We can have areas with gentle slopes that allow snow and ice to accumulate, but in areas that are more steep in elevation, snow and ice may slide downhill. So glaciers flow from higher elevations to lower ones under gravity. And of course, they can merge, becoming wider and thicker over time. Whether or not a glacier will form is going to depend on how much snowfall you get, the temperature, the direction that the glacier faces. Like, it's more likely to form on a north face, colder face, not in the sun all the time, and the steepness of the slopes. So we have these huge glaciers in Washington where it's actually warmer than, say, Montana. Montana glaciers are smaller. Montana glaciers aren't building up as much because they don't have as much precipitation as what you get along like coastal Washington. Okay, so glaciers in the landscape. They can flow downhill, right? So glacier blue ice flows down a steep valley and ends in a lake. And then crevasses form where glaciers flow around a bend. So cracks, crevasses, they form due to flow. They're very dangerous. If you're walking on a glacier, you can fall in one, right? The lower parts could be blue ice. Typically, this looks very bluish in color. Okay, so glaciers can pluck away pieces of bedrock. Right, they can grind up some rock into fine rock powder, and they typically will have these dark fringes along their margins. We can have moraines form there. The end of them, of course, we call that a terminus. They can flow onto water and sort of sit on the water as an ice shelf. When they break off pieces, those are just icebergs, and they're no longer a glacier. The icebergs might come from a glacier, but they're no longer the glacier, okay? So broadly, we have a few different types of glaciers. You can have an ice sheet. Those are regionally continuous masses of ice, and some of those can spill over cliffs, like in the case of Antarctica. You can also have valley glaciers. Those form between mountains at areas of lower elevation. They flow down valleys, right? And they tend to be very narrow. But then as valley glaciers flow out of a mountain into broader topography, they could form what's called a Piedmont glacier. And that's sort of a delta-shaped glacier as they leave the mountain range to an area of lower elevation. So where are most ice sheets and glaciers? Well, at the poles, really, where it's coldest. You've got Antarctica covered in glacial ice. You've got sea ice and then ice sheets in Greenland. Iceland has plenty of glaciers still. The Alps, Alaska, and the Rockies, the northern Rocky Mountains, and Tibet, and the Himalayas. Okay. You have to have sufficient precipitation and cold enough temperatures to create these things. So how does snow and ice accumulate in glaciers? Well, snowflakes are pressed together by the weight of other snowflakes that pile on top of them. Right? They become more dense. More snow adds weight and compresses snowflakes into smaller spheres. And they actually changed like their crystal shape with increasing depth and pressure. It causes the snow to become crystalline ice, and it looks bluish because it has trapped air in it. So we'll look at how a glacier forms and changes as it moves downhill. Okay. A glacier is going to form where an accumulation of snow and ice exceeds loss through melting. So this is our zone of accumulation. Got snow. The glacier loses ice and snow by melting, wind erosion, and sublimation. Okay, so this is our equilibrium line where we're gaining, we're losing down here, and this is where we're kind of at a standstill. That's the equilibrium line. And as the glacier moves downhill, the loss of ice and snow due to melting, it's in an exact balance with the amount of accumulation. Again, the equilibrium line. At a lower elevation, the ice melts faster than it's replenished, and that causes glaciers to terminate. That's the terminus of the glacier. We call this the zone of ablation, where we're losing the glacier naturally. And then ice melts at lower elevations on land or in the water. This would be like a cartoony cross section of a glacier. So further up the mountain, you have your zone of accumulation where you're gaining ice through precipitation, net gain. And then further down in elevation, you have net loss. You're losing more than you're gaining. Where we have neither gain nor loss, that's our equilibrium line. We actually can see that in the summer mostly. Okay. So how do they move? Glaciers move by slipping along their base underneath them and internal shearing and flow of ice crystals. So when a glacier is in a warmer condition, there's more water underneath it and it can move faster. We call that like surging. But gravity pulls the glacier downhill. Friction along the base causes the bottom of the glacier to lag, and that would slow it down. And then the upper part is going to flow faster than the lower part, which would cause internal shearing. If, say, the interface of the glacier and the bedrock is smoother, the glacier may be able to slide over the bedrock faster. Okay, so irregular dry interface between the bedrock and the glacier, it might lock it in due to friction. If you add water, if you have smoother bedrock, that glacier is going to surge or slide forward. So what happens when a glacier encounters water? You have our glacier here. We call it calving, actually, because it's like the glacier is giving birth to these little icebergs that break off it when it hits water. It's common in an actively moving glacier. It doesn't indicate that the glacier itself is melting or retreating, but this is kind of a dynamic area. You can have ice blocks, icebergs, and falling stones. And the glacier may begin to float on water. The floating ice spreads and fractures and creates all of these things in calving. You can have, large blocks collapsing off the glacier as well, and then become smaller little icebergs that travel around the ocean until they melt. Okay, so erosion due to a glacier. I've talked about all the sediments that can be associated with a glacier, but they get these sediments because they carry rocks and other debris with them that can erode underlying materials like bedrock. They can abrade and smooth off bedrock that's in their way. Be very destructive, I guess. They've shaped a lot of features in Michigan. So striations, this is in Marquette, Michigan, from your textbook. That shows, our direction of glacier movement all in one line here. Unidirectional, I should say. We have grooves as well from Ohio. Those are pretty cool. And then this is the direction of ice flow. You can't really say it that well because we have a very eroded piece of rock here. But understand that striations generally can indicate the direction of ice movement. But there can be a little more to it than that. We won't go into that in this lecture. You can also have something called plucking, and that occurs on the down ice side of the bedrock with obstructions and striations on the up ice side. Okay. This is a subglacial channel. Kind of would make me nervous to go in it, but you've got all this debris and then flowing water and then glacier ice up above. So let's talk about glacial transport. So glaciers transport material at the surface, at their surface, right? This is the surface. Their interior end glacial, we call that. And then their base, we call that subglacial. And then the surface would be supraglacial, like on top of it. So on top of the glacier, this is from the Muldrow Glacier in Alaska. The material that's carried by the glacier, it's very dirty. Like I said, don't drink from a glacier unless you want to drink dirt. Within the glacier, end glacial, and then below the glacier. Very cool to see. I gave you my basic like glacial lake deposits. We'll look at these as well. So these are also deposits of glacial origin. This is from, valley glaciers in a mountain. You've got this huge fat moraine at the terminus of a glacier. You can have glaciofluvial outwash, like a little stream coming off a glacier carrying a lot of debris, and it's quite angular because it's near the source. The mountain is the sediment source. You can have till as well, which is like a diamicton sediment of different sizes. And then in a glacial stream or even in a glacial lake, you can have glaciofluvial deposits like sand and a little bit of gravel. All right. Features formed by glacial erosion. So we'll start off up high. Cirques. It's like this concave circular feature. You can have a cirque glacier in a mountain like this. It's formed in part by plucking rocks by the glacier. And then small lakes formed at the base of the cirque are called tarns. You could have a series of lakes along a glacial valley. Those are called paternoster lakes. You can also have an arête. It's a jagged and steep feature because we have glacial erosion from both sides. You can see U-shaped valleys from glaciers or like saddles on mountains. Perhaps you're familiar with what a saddle looks like a horse saddle, but on a mountain. A fjord from a valley glacier or a hanging valley. So features formed by glacial deposition, again, they include moraines. You can have a moraine in the middle. You can have it lateral to the glacier, or you can have it at the terminus. And we know that glaciers carry rocks. So looking at this, what do you observe? Like, we don't have glaciers here anymore, but we would have had these valley glaciers here. We've got these strong ridges, sedimentation, like moraines here as well. That's from the Sawtooth Mountains in Idaho. So like lateral moraines, terminal moraines, all associated with the glacier. So let's go back to ice sheets. So landscape features of continental ice sheets. Got this big ice sheet here and a ground moraine associated with the glacier. We have something I haven't mentioned yet, an esker. That's a winding ridge of sediment. It's the former position of a subglacial channel within ice. So I showed you those where I said you could walk into them and the ice is on top, and kind of scary actually. I don't want to walk in there. A lot of these in Michigan are mined out for their sand and gravel. So we know where they were, but now they're gone because they're very useful to say things like road construction. You can have kettle lakes. Those are essentially what happens when you have a block of ice that sits on the land surface, depresses the land surface and melts. A lot of our lakes are this because of glacial ice. Like imagine pressing an ice cube into some beach sand, letting it melt. You'll form a little analog to a kettle lake. see. You can have these drumlins that form parallel to the direction of ice advance due to heterogeneities in sediment. And then recessional moraines, terminal moraines. As the glacier melts, it leaves those sediments. So kind of peripheral to glaciers, you can have an outwash plain. That's a glacially produced sediment that mixes with meltwater to form large rivers loaded with sediment. And then the rivers deposit sediment on a broad outwash plain. You can also have loess, it's called. So glaciers pulverize the rocks below as they carry the rocks they move over. That produces silt-sized materials that can be blown away by the wind. This is in China. You can also have permafrost. So that's permanently frozen ground. This is in Denali National Park, Alaska. In the warm months, the top few meters could thaw, allowing vegetation to grow. Fun fact, our ancient ice sheet that I showed you in the second slide, pieces of it are still encased in the permafrost in like Canada. It's still there for now. So this is where we see permafrost zones continuously, discontinuously, sporadic, and then isolated as you move south. It's restricted to northern Canada and Alaska because that's cold enough. Okay, so lakes formed during glacial times. This is kind of cool. So I used to live around here, and this area is definitely shaped not only by tectonic forces, but then later these glacial features. Okay, so Lake Missoula, that's an ice age lake that filled low interconnected basins in the Rocky Mountains of western Montana. It got dammed up by ice, but when that ice dam broke, we had catastrophic flooding all over here. It created the channeled scablands. So Lake Lahontan, that's a large ancestral lake that filled the low basins of western Nevada. It was up to 240 meters deep about 13,000 years ago. And then Lake Bonneville. The Great Salt Lake is a remnant of Lake Bonneville. It was an ice age lake in northern Utah. So we have these Lake Missoula shorelines that we can see now still, and then the Bonneville Salt Flats. I'll go through this quickly. So how did the channeled scablands form? All right, so we had like an ice dam on this kind of complex glacial Lake Missoula. At a certain point, that dam broke and then flooded all the way, throughout the west here in purple. Okay, this is like a catastrophic event that was debated by geologists for quite a bit of time because people said you couldn't so quickly have like these scablands form. But the current data supports the theory that these were formed by an ice dam break. They gave us these giant potholes as well with the floodwaters and giant ripple marks. All right, and then the evidence that we have of past glaciations includes, of course, all these glacial landscape features that we talked about. The polished surfaces of rocks that we see with glacial striations. Something that's also a favorite of mine in Michigan, we call these glacial erratics, like boulders that aren't from here. They were transported by glaciers and then they were just deposited here, like granite from northern Canada and the Canadian Shield. So we also have like a graph here showing our oxygen isotope composition of marine shells. If you have a higher ratio of delta 18O to delta 16O, that's our glacial period. Our data indicate that glaciers increased and decreased in volume many times over the past 2 million years. Call that interglacial periods where things warmed up a bit, then got colder, built up the glaciers, warmed up again. You know, it was very cyclical over the last 2 million years. So today, this is our ice. We're still in the ice age. It's just much smaller. But for some reason, that makes me happy to say. And then 28,000 years ago, we had so much more ice. Not everywhere, though. Not the whole planet, right? So in North America, we had the Laurentide ice sheet and the Cordilleran ice sheet. 28,000 years ago, then 11,000 years ago. And zooming in on what we looked at in earlier slides, you know, these ridges are moraines. These features were left behind by the continental glaciers. And glacially smooth troughs, recessional moraines. And then rough, non-glaciated areas. Because like I said, the ice wasn't everywhere. Our glaciers flowed parallel to smooth troughs. Right? So we even see moraines on Long Island and on Cape Cod. So glacially smooth areas and recessional and terminal moraines. And we'll stop here for today. We'll pick up with how changes in the Earth's tilt and temperatures will influence global glaciations and get into more things about sea level and how glaciers might relate to that as well.